Okay, so nice to meet you, everyone. I'm Lia Song from University of Adelaide, and machine learning is my research topic. And recently, we have a collaboration project with Alison and Theo on the machine learning class XR system. So before I going forward, I would like to ask you about your understanding on machine learning and some other hot terminologies, like what is the difference between machine learning and deep learning? Are they the same or different? What's the difference between deep learning and large language models and deep learning with neural networks? Do you all know the difference between these terminologies? So starting from the first one, what's the difference between deep learning and machine learning? Yeah.
No, I'm not putting my head. One's inside the other.
Okay. Do you have any background or do you have any practices on the machine learning by yourselves? Then, for these people, also for the student, you already have get some experience by self-study. Then my first question is, what is the difference between machine learning and deep learning?
Deep learning is a subset of machine learning.
Correct. Deep learning is a subset of machine learning, and do you know why it is a subset? Okay. Then the second question is, what is a model? What a model takes a role in the machine learning procedure or machine learning tasks? What is a model? Sorry?
It's a function.
A function and
It takes a data.
data. And takes data as what? As input. So it is a function, it takes data as an input. Okay, so you might have heard a lot of different machine learning models where the neural network is the most famous one, right? Then what is the difference between machine learning and deep learning? Is a difference between what is neural network with deep neural network. Anyone knows the difference between neural networks and deep neural networks?
I'd just say the size.
Say the size.
Yeah, that's the complexity.
The complexity. Correct. Actually, correct. Very correct. The difference between neural network and deep neural network is the deep neural networks, they have more layers and they are more complex in its architecture, modeling architecture. But all the deep neural networks, they are all neural networks. Similarly, all the deep learning methods, they are all machine learning methods. So last question, what's the difference between LLMs, large language models, with others? Any insights? And if you think about these questions, what's the difference between large language models with deep learning models? And why we not just saying deep learning models? We always saying large language models. Is that has to be language models rather than other models? Do we have large vision models? Do we have other like large speech models and so on?
So the large language model, the training data is text modality, and it's a generative model. So, like the output is generate by generation.
Okay, so that is one understanding of the large language model. Large language model especially handles language data, and it is a generative model. That means it's generating something rather than outputting a specific fixed format, right? Then the question is, do we have large video model? Do we have large image model? Do we have large speech model? Yeah, for sure. Which we call foundation models, but however, we always use large language model to replace this foundation model because the first foundation model, they are language model. Okay, so these are some basic definition under machine learning and why we sorry.
Up to 10 minutes.
And let's see how it comes to how the machine learning should be. It is truly applied to application, especially in today. In this lecture, we focus on XR application, right? We know these different machine learning methods and different machine learning models, and we know, for example, the deep learning model should be more powerful than the classic like shallow machine learning model. And the large language model should be even more powerful than the deep learning model because it treats with hundreds, like a large amount of data. The model is very, very complex than just a classic deep learning model.
Oh, okay. So the next session has started. You
Means
can join
we
maybe.
should always use this advanced, more complex model in the real application.
And
Depends why.
some use case maybe need very quick real time
Yeah.
answer.
Oh,
Okay,
okay,
so
okay.
you mean the more complex data, they can't answer the questions in real time with prompt replies.
Good.
That's one of its
Yeah, I will
disadvantage of these
forward
very
that
large
anyway.
models.
I
Right,
think
so
the next
do you
session has
believe
started,
the
Manny, so we
accuracy
can
of
join
large
that.
model or the quality of the large language model is
Okay,
more
bye-bye.
accurate than the classic or the normal deep learning model, right? If we don't consider the time cost is one of the reasons that we don't use these models.
Also depends on the task. If you kind of like tabular data or like very specific data form factors, then the LM maybe not that good as traditional method.
Okay, so given the case that we are handling text and we don't consider time is our the factor that influence the use of these models, you will think the large language model is always the best solution compared to other machine learning methods, right? Anyone have other opinions? Okay, so by this project and by today's lecture, I'm going to give you an example of a large language model failures, not just a failure by its time cost, but also failure in its accuracy. And let's see why in a specific application, even such powerful machine learning model can fail, and how we can like edit the model, or we can do some special design to address these questions or address these challenges, and where these challenges from. This challenging from your real applications, because for each of these customized application, your data is specialized, your task requirements is specialized. That means your model needs some special design. Okay, so following Alison's slides, we have this project, and what's the aim of our project? We found from existing study from the XR collaboration, we found that these gate queues can actually enhance the XR collaborations, right? And what's the difference of these gate queues in real face-to-face collaboration to the collaboration in the remote environment? So if we are, for example, chatting face-to-face, you might know my gaze. You might know my gaze by just watching or observation, right? However, in a remote collaboration, we don't have this face-to-face convenience to know that gaze cues, right? However, we still, especially in some previous study, we found these gaze cues are actually very useful of enhancing the effectiveness or enhancing the collaboration understanding during when there are multiple users in collaborating to complete one task. And that's why we are thinking, oh, how can we indicate or how can we infer these
Hello.
skills in a remote collaboration environment so that our users, when they are
It's probably
either
easiest
playing
talk
games or
through
either
whether they would be
completing a task
suitable
in
or
this
not, rather than
XR
like hearing
collaboration, they can
or
still
feeling
use
them,
this gate skill
like
as
it's
smooth
acceptable.
as when they are completing this task in the real world, in the physical world. So that is summarized to to the introduction of this project. Like we would like to apply or we would like to infer these gate cues to enhance the XR collaboration. By how? We can't. In previous study, we have designed some rule-based systems, which is not that accurate than random guess. That's why here we are wondering, can we borrow the poverty of large language model or machine learning models to make this happen? So eventually, we designed this machine learning architecture or these machine learning models to implement such idea. Like we design a machine learning model, and we use this model to infer this gaze queue. And this inferred gaze queue can then be embedded in the system by some system design, right? Because for the pure machine learning model, it can't be appeared directly in your system. The pure machine learning model can only output a value of gaze or non-gaze. However, how we can leverage this information of gaze or non-gaze that can eventually enhance the XR collaboration. So that needs your understanding of system design. So in this project, we eventually build this gaze on and gaze off signal as a ball in the system. Rather than showing them always, we're showing them only when the user needs. So actually, this machine learning model is not to predict whether people are gazing. Actually, indeed, users are always gazing something, right? So for this machine learning model in this project, it actually predicts when the gaze on is needed or when the gaze on, this information is required or can enhance the collaboration, right? So that's the overall of this product, of this project. And we have the input, which is the speech of the users, the dialogue of these users. And we have the output of either this speech, this dialogue, indicate a gaze on or off gaze, but indicate whether gaze, this information is useful or not. So instead of going through every of this module, I will use a more simpler structure to help you understand what is a classic machine learning model. So this is our machine learning model with its input, with its output. For students or for people you are familiar with machine learning procedure, you might exactly know what is a ReLU, what is a fully connected layer. However, for other students, you don't have to know these details because for your task, you might need something else, right? So here, I would more like you to understand what is the more general structure of a machine learning model and how machine learning models, they receive input and they calculate the output. So the input of this project is our speech between users. And what is the output of this project? We would like this learning model can output a signal of should we present gaze or should we not present gaze, right? Through what? Through a machine learning model. So here I just combine them together as a model. And what you need to learn is, we need some special model design so that it can eventually receive the input of speech and output the gaze or non-gaze. Okay. We know model, but we don't know design, right? This is for every task. We need some special design that especially fit your task and how we design. So at the beginning, we introduced so many different machine learning models. The very classic one, very simple one, the deep learning one, deep neural network one, or the large language model. So we started this project at 2024, where the large language model already showed very powerful ability to handle different text-based tasks. That's why at the beginning we think, maybe we can directly embed a large language model to address this problem. However, eventually we found there are some flaws or some drawbacks, disadvantages of the large language model. That's why we eventually use a classic machine learning model. However, this classic machine learning model have some special design, it has some special design that include a part of the machine learning, part of large language model component. And let's see step by step how these eventual classic machine learning model is motivated step by step. So we first think, oh, given that large language model is a very powerful model, can we directly apply it to our system? So this will be our initial attempt, right? We have the input, we have the output, we use a large language model, and how we can use a large language model? We use prompt, right? This is everyone knows. So the prompt here is, okay, given a large language model some prompt, like, oh, here is the sentence, and we input the user's speech as the sentence, and could you output me the gaze or non-gaze label? So we ask the language model to make inference of and outputting us the result of gaze or non-gaze. However, we found direct. At that time, GPT-4 is the most powerful large language model. However, even with GPT-4, we found the accuracy is not as good as we expected, and it is very sensitive. Sometimes it gives you very good result. However, sometimes it gives you very bad result. This is something that unacceptable, and also it has the latency problem. Like we need to wait for 3 to 5 seconds to get this inference. And what are the other potential risks? One is the cost, right? We call the API with some money. And the other is because you need to call this API online, right? What if when you are implementing your experiment, the Wi-Fi is suddenly gone, or there is some disconnection between you and the internet, then all your experiment just ruined at one time, right? So that is some drawbacks of directly using these large language models. Actually, after our initial try, even we got that failure, we think, oh, maybe we can still believe the large language models. We use that in a different way. So that is, we refine our prompting. I don't know whether you know the prompt engineering or the most recent context engineering. Actually, here we do some context engineering. What is that? So instead, let's just compare these two. Instead of directly asking this question of, oh, here is a user's speech, and could you give me the inference of answer of gaze or non-gaze? Instead of asking that, we first give this large language model. Here are some examples of the gaze or non-gaze example we accepted. By in this context, could you then infer whether this user speech is a gaze or non-gaze? Anyone have any questions here? I believe when you're asking your GPTs, if you change a way to ask it with different prompt, or sometimes if you give them the context, right? When you're asking your GPT to give you some code, right? You can ask him, for example, I am a developer and this is my task. Or you can ask them, I am a manager, this is my role, and I want some code. The GPT will give you different answer based on the different context you give it. And after we have this refined prompting, we found, oh, the accuracy has been improved by 10%. However, it has larger latency, right? Previously, it is 3 to 5 seconds, and now it is 5 to 7 seconds. And it means more costly. Why? Because you input more data to it. That's why it needs more time for inference. And because you input more text, it costs you more tokens.
Yeah, there's a question online. Josh is saying, how do you structure your measurement of accuracy Was the same set of speech input repeated, and how many samples did you use?
You mean in the when we directly use the GPT-4?
Yeah.
We directly, I think we use the previous data collected from Allison's experiment. There is 6 groups, and we use 3 of them and the other 3 for testing. And we use this cross-validation method.
So how many speech samples did you put in?
How many speech samples? Alison, do you know how many speech samples in total? I think
A lot, hundreds of hours.
100 of hours.
So how many phrases was there? Like 100 phrases or 200 phrases?
I can't remember on top of my head. It's just basically each study is like 2 hours conversation. Can be more, can be less depending on the pair. So it's like hundreds of hours of conversation. Can be more, can be less. I don't know the exact number.
Any other questions? Okay. So this is our second trial using large language model. We found it still can't fit our problem exactly. That's why we review. Because the latency is a big problem, big issue in this project. Can we overcome these drawbacks to, instead of using some online models like these online large language models by API call, design some local machine learning model that we can call locally to largely reduce these time delays. And this is how we do that, because let's review these tasks. We have input, we have output. This output is kind of label of gaze or non-gaze. So naively, simply, it can be considered as a supervised learning tasks. So what is a supervised learning task? For example, if we have the machine learning model, trained machine learning model, and we know this model can identify a dog from a cat. And when we input a dog when we input a cat image to this learned machine learning model, it can give you the output of whether this input is a cat or a dog. So similarly, in our task, if we have a learned machine learning model, it can identify gaze from non-gaze. Then when we input any speech, apply this learned model, it will give us the output of gazing or non-gazing, right? So the question is how to learn this machine learning model. So how to learn this machine learning model? We need to go inside of what is machine learning, the procedure of machine learning. A very typical machine learning procedure is we first train a model from our training data. This procedure is called training. We use a bunch of data, which this data include the features as well as corresponding label. So in our case, the feature is a speech, the vectorized speech, and the label is gaze or non-gaze. And after we train it, we get a model. And after we have this learned model, we directly apply this model to answer some question. So here the question would be, given this speech, what is the output or what is the label of that speech? One highlight here is in the training and in the testing, we all have the data, right? Because when we answer the questions, we always input a data. However, in the training data includes known input and output. That means we have the input and output pairs. However, in the testing, we only have the known input, like we only have the speech. However, we don't know its label. So that is the difference of data during the training and testing procedure. And this is a very classic supervised learning, machine learning procedure. And later on, I will share a practice document. We can, for everyone, no matter whether you have learned machine learning, whether you know Python, but by that practice, you can try it a little bit of how a very toy sample is, how we train a model from a toy sample and how we apply that trained model to unknown data. So this is later on, but what I would like to go further is in the training, how the model is trained. For sure, we need to have the data, the historical data to train this model. What else we should have? Actually, in machine learning, this is some knowledge that some people may overlook. Instead, in addition to the training data, we also need some prior knowledge. Otherwise, you will not train your model. What are the required prior knowledge? We should have an initial model. So what this initial model means we have a prior knowledge of the architecture of your model. For example, at the beginning, before you training this model, you should determine what kind of model you are going to train, whether it is a linear model, whether it is a SVM model, whether it is a tree model, whether it is neural network model. You can't just randomly say, oh, train a model to the machine learning algorithms. And you can't get a neural network model if your initial model is a linear model. That's why when you train your model, you should have data and you should also have that prior knowledge and how these training procedures. Like we have the initial model with special format, for example, linear model. What information we are training or what we are learning. What is the difference between this initial model and the preferred model? So in machine learning, we have the prior knowledge of this initial model. However, we don't know the best parameters in this model that best fit your training data. So machine learning is to learn with this data, like we gradually adjust our model from the initial model to the preferred, the optimal model so that it can perform best on your data. That is why machine learning is data-driven. But this data-driven has a prior knowledge of what kind of data you are training. Okay, so with that knowledge, we can simply split the training testing procedure into the following steps, right? During the training, one important thing is we need to have the data, and the other thing is we need to have the prior knowledge of, what type of data, or what kind of model we are going to optimize, right? Then after we determine that, we just randomly give this initial model some parameters. So these two steps will consist our initial model. And after that, with this prepared data, we use data to update these initialized parameters to achieve these parameters optimal values. So that is the procedure of machine learning training procedure. And after that, to step 2.3, we have this optimized value of these parameters, right? And we save these parameters with its structure as the final learned model. So we save the preferred model. That is how preferred model is coming out. And during the testing, because we already have this preferred model saved, we just load this saved model and we input the new data and we can output its label. So this is machine learning. And we always say we use Python to implement this machine learning algorithm. All the machine learning toolkits are always built with Python. So what makes Python and machine learning, they connect with each other so deep? That's what I'm going to discuss about using the Python to implement machine learning. The benefits of using here the title is using Python to implement machine learning. What are the benefits? For sure, you can use other coding language like C++, Java to implement these learning ideas. Even Python is a coding language. It just simply implements some functions. However, why we largely use Python to implement machine learning? Because for Python, there are a bunch of existing researchers, they already write down these coding functions and package it as Python libraries for you to directly download, directly call, so that you don't need to write down your own. That's why we largely use these Python libraries for us to implement this machine learning or handle these machine learning tasks. And there are a lot of online resources for you to practice using Python. That's why in most cases, we use Python to implement machine learning. Even with today's practice, I prepare a Python-based Jupyter notebook for you to practice a very simple supervised learning, a very small project. Because we have limited time, I will skip this to the next part, and if we have time left, we go back to this practice document. Okay, assume that, after this practice, given that data, and we choose a specific machine learning model, and with that data, we eventually learned the optimal model, and we apply that model to testing data. Assume that you already know that. The next question of this whole project is, okay, in this project, how can we obtain our training data? Do we have existing historical data of non-gaze or gaze data? No, right. So that is why in this project, in addition to we design a local machine learning model, we also use a socket. So what this socket is for? This socket is to save some training data for our use, to save some good qualified training data so that our designed local model can train to a preferred machine learning model and when we embed this trained model into the system, it can achieve very good results. So how can we collect, or how can we create this good socket? We use a large language model. Remember previously when we try large language model with a refined prompt, the accuracy increase, and the only drawback of that language model is the cost and the time delays, right? That means for that large language model, it helps us to accurately extract some information from the speech. However, we can't use that because even we use that information in this online deployment way, it causes a lot of cost and the time delay issue. That's why, we change our stuff. Can we make that online created, extracted information into local? So that's the idea of having this socket, and this socket is a pool of manually converted data which contains, that means we manually created this one. Although it is manually created, it does not mean that we created one by one. We created by scale. Like we create a pair of supervised learning samples with each sample represent a vectorized speech, and the label is coming from the refined prompt LLM. Why? Because we don't have the ground truth of whether that user is gaze or non-gaze, right? That data, the original speech data, is collected from Alice's previous project. And clearly, in her previous project, we can't always asking our user, are you gazing or are you not gazing? Especially in this project, what we are predicting is not just simply gazing or not gazing. We are actually predicting whether this gazing information is beneficial for collaboration, which the ground truth is never been observed, right? That's why here the refined prompt plus LLM is still useful, even you build a local machine learning model. So in this project, we show a case study of how we combine a new way of using LLM and to avoid its drawbacks and largely leverage its powerful inference ability and eventually combine everything into this XR collaboration project. Okay, so that's the whole overview of this project. And let's go back to this machine learning, supervised learning practice. So in the chatbot, any questions here? Yes.
I have a question. So I'm just curious, maybe I missed something. So you used the speech data from Alice's project, right?
Yes.
The question is, I think you supervise learning, and why don't you combine those with the visual data as well, and use different model and supervised learning?
You mean why we only use speech rather than multimodality?
Yes, correct.
Because this is first step that we try to combine LLM and XR. We don't know about the result. Our next step is to try multimodality data.
Okay.
Yeah, that's a very good question. Why we only choose speech? Because this is research. Like we can't at the beginning we can't consider all of them. We just try one by one. Any other? Yes.
Is that because you don't have camera access? So you've started at the base. You don't have camera access or to take in the visual data?
Alison, do we have the camera access? I think we have the camera access.
Yeah, we have all the physical data, but they were not really synchronized together and it wasn't really labeled at the very beginning. So we only have the text. Yeah, once it's done, then we can have the second step.
Yes, I remember why we didn't try the visual data because in Alison's project, because when she conducted her project, it's not designed for combined machine learning. So her data is like, oh, this is a speech, and the other data is I think captured by camera, but we can't exactly align them by timeline. Yes.
Question from George. So for example, if later on you want to use the multimodal data, right? Are you going to collect another set of data or are you going to go back to your previous data?
Actually, for in this project, actually we already prepare our next step. So when E is conducting this project, we collected the synchronized data. And in the future study, we will use the data from E's project to conduct the research on how the multimodality data with machine learning can eventually enhance the XR collaborations. Yes.
So you don't have to label. So the label dataset is a synthetic dataset generated by LLM.
Yes.
So how do you evaluate this? Like it's represent the real world performance, and like how do you know that it's aligned with the real world?
So for the model size, how we evaluate this model, we evaluate
model is like how this data represent the real world.
Person's reaction.
We use user study, like we recruit new participant and control the conditions, which is not exactly my expertise, but the procedure from my understanding is we recruit new participant and we design we design one system but with 3 different control variables. And in that each control variable, for example, in the first one, no LLM or machine learning is embedded. In the second one, the LLM is embedded, and for the last one, the machine learning is embedded, and we record their user behaviors, like how long they complete this task and their feedbacks to the systems, to evaluate.
Okay, so the non-LM embedded group is labeled by human.
Do you mean the non-LLM group? What is non-LLM group?
Like you mentioned, there's 3 different groups. So there's a one first is non-LM group. So what I mean is, how do you evaluate this data set is valid, is like related to the real world? Like this is non-gazing and gazing. like why this label generated by LLM is represent the real world.
Alison, do you understand this question?
He was talking about two different things. I think he was talking about the label from the previous training data set, which we do have a label. We have conditions which we know which one has gaze, which one doesn't. It's just we didn't label each single phrase. So the conversations within this without gaze system. So we're talking without the gaze, and then we recorded all the conversations, we transcribed them to TXT file, and that data was used to train the model and also tested with the model that's already been trained. I think that's the part you're at, right? Not the later part. Yeah. So they were real world scenarios in an actual setting that consists of two people having the conversation with or without gaze. That's labeled. So those are with gaze, those are without gaze, that's labeled. And then the data was trained to the MLP model that Lia and Yi was working together on.
Okay, so the data set, the label from the data set is not just synthetic. It's not.
No, they were genuinely no gaze versus
Okay.
gaze.
Okay.
Yeah.
I think at that moment, the gaze and non-gaze is labeled by you, right?
It was labeled by the condition. Yeah, we had
Oh.
different conditions. Two has gaze, the other two doesn't. Everything that has a gaze was labeled as with gaze condition.
Okay.
So that was how it's labeled. It wasn't synthetic.
Okay. I see.
Okay, that's all. And for the practice, could you just download this Google file? I just share a Google Drive link, and you can download that practice document and practice by yourself of how a very simple supervised learning task it is. Let me just stop sharing. So if you download that document, you will find that is so that is a practice exactly implement different stage of a supervised machine learning procedure. And especially here, I expanded the preparing this step 1 a little bit. I implemented the training with only like 2 or 3 lines of code and testing maybe another 2-3 lines code. So here, by exploring this practice document, you can so for your practice document, you only have the questions rather than the solutions, but later on I will send these solutions to Mark as well. So you just run them one by one. Here, so if you have noticed that before we before we answer all the questions, the first step always we import these related libraries. And why we use the Google Colab? Because in the Google Colab, you can consider it as an online platform already embed all the related libraries. If you want to run it on your local machine, when you import these libraries, you have to install these libraries, namely download all the functions and classes included in these libraries into your local machine so that you can run it in your local machine. However, if you run this via Google Colab, there is already being, you can consider all these libraries already being installed in the online environment, you can directly import. And after you import every of these libraries, for example, if you import this pandas as PD, and you can simply call this, for example, you simply call this library as PD. That's all. I don't think I have enough time to go through the practice. You can just run the practice by yourself. And if you have any questions about the coding part, a very useful tip is just input it to the GPT and asking the GPT, oh, what these codes are for. However, one of my suggestions is if you really want to learn more in machine learning, after you implement every of this code, it is better for you to search. For example, you search, oh, what this function is exactly looking for. So all the libraries, they provide very detailed documents, tutorials for you to referring to, oh, what are the parameters, what are the input of each of these functions, and what these functions or the classes is doing. Okay, that's all. Thank you.